And I'm going to oops. Okay. So we're going to actually get into more classical chemistry in Unit 2. Unit 1 was kind of almost like a math class. It didn't have a lot of chemistry there. But now we're getting into real life chemistry stuff. Okay. When you're in a chemistry class, you need to know if a chemical change is happening. There's a lot of things going on whenever there's a chemical change, but basically what we start with are called reactions. Something happens to those reactants, and products form. Okay, now we know the products are formed because things like we see gas bubbles, we get a change in color, we get things solidify out, we get two different phases, maybe excuse me, an oil layer and a water layer. Something changes. Something changes, and visually, or some kind of subjective, whether it smells differently, visually we see bubbles forming, a solid form, something happens. Then we know a reaction has taken place. Okay, if a reaction takes place, chemical bonds are broken. This is chemical bonds now. And then chemical bonds are reformed. Oops, okay, so bonds are broken, bonds are reformed. So if we look at this reaction here, we have water, and when water is broken apart, it gets broken into hydrogen gas and oxygen gas. Okay, so this is what water looks like. So in this situation here, this bond is broken. And these bonds are reformed. Now, what's important, this requires energy, because we have to break those bonds in the reactants. So you just can't start something on its own. It's got to have energy. Now, the energy may come in the form of ambient temperature that could supply the energy, or we could have, like when we have a match, we have to strike it before it'll light up. If we have a piece of wood, it just doesn't spontaneously go into a fire. We have to light it with something and get it going first. So all these are forms of entering energy into this chemical reaction. Now, what we're going to do now is we're going to look at this graphically. Does this make sense, by the way, so far? Are we okay? Okay. Now let's look at this from a graphical perspective. I'm going to graph energy. And the kind of energy I'm going to be graphing is something called potential energy. Now there's two basic kinds of energy in our universe. There's potential energy and kinetic energy. Think of kinetic energy as the energy of motion. Potential energy is the energy of position, usually. Okay, so in a chemical reaction, we have this possesses both kinetic energy and potential energy. There's another factor in there I'm going to talk about later. It's called entropy. We're not going to talk about that now. So, which also is included in here as well. Okay, so we have everything has a combination of kinetic and potential. What happens during a chemical reaction is we end up with each molecule ending up with kinetic energy and potential energy. Now the deal is this has to be equal to that. So we conserve energy in a chemical reaction. Excuse me. Now, Einstein says, well, we can interconvert mass and energy as well. So sometimes in a nuclear reaction, we lose mass and it's converted to energy. But unless we're talking about a nuclear reaction, this comes into play, but not to any significance. So we're not going to worry about that relationship here in this class, at least for these arguments we're talking about today. Okay, so Einstein said we can interconvert energy and mass, and it's through the speed of light squared. So that speed of light squared is quite a large number, and then it's squared so that the amount of energy consumed when mass disappears is quite large. That's why an atomic reaction or a nuclear reaction is so horrendous, the amount of energy being given off, because we're losing mass. Okay, so back up to here. So we're going to start with a certain amount of kinetic energy and a certain amount of potential energy, and then something's going to happen. Bonds are broken, bonds are reformed, and then we're going to end up with kinetic energy, potential energy as well. And those are going to be equal. So the reactants, products, energy-wise are going to be equal. Now the manifestation of this, let's remove this for the time being here. So I mentioned kinetic energy is the energy of motion. That is manifested in itself in a chemistry environment as temperature. So temperature is a measurement of kinetic energy. It's measured in either Fahrenheit, Celsius, Kelvin, Rankine. different temperature units, but temperature is a measurement of movement of a molecule. So the more the molecule moves, higher temperature. Now, there are a lot of modalities of motion for these molecules. They can spin, they can vibrate, they can move from one location to the next. All those are modalities of motion that are manifested and measured by temperature. Okay, so this basic concept here now. Energy has to be equal. Okay, does that make sense? All right, so let's now zoom back over to here. And let's look at now, from a graphic perspective, of a graph of potential energy in terms of reactants and products. Okay. Usually when these graphs are done, they always graph something called G. And G is potential energy plus entropy. And the entropy takes into account some randomness factors. But we're going to talk about just potential energy for now because it's an easier concept to understand. And one thing I forgot to mention here. Potential energy is they usually say is the energy of position. And it's position relative to a force field. But what we're talking about here is bonds, chemical bonds. Because the chemical bonds have all kinds of forces going on, keeping them in place. And it's we're going to talk a lot about that in this class. But for right now, think of potential energy as chemical bonds. Okay, so we have reactants. Remember, we have water is broken into oxygen gas and hydrogen gas. Okay, and that's going to be a certain level of potential energy. Now, for a reaction to happen, we have to create something that, excuse me, not reactants, I meant products. Reactants, excuse me. I was thinking ahead of myself. For a reaction to happen, we have to get something that's more stable than what we started with. The universe is like that. If it's not more stable than what you started with, it won't happen. It's kind of like a long-term relationship. It's got to be more stable in the long term, otherwise it's not going to happen long term. Okay, same with chemistry. We have reactants and we have products. Okay. Things that are more stable have lower potential energy than things that are unstable. So if we're going to have products that are more stable than reactants, the potential energy needs to be less. Now this is the sum of all the reactants. You can have 20 molecules, you can have one. Products, same thing. 20 molecules, you can have one. It's the sum of all the reactants, the sum of all the products. The products have to be more stable than the reactants. Now, I'm going to be saying this for the whole semester. stability rules the game. Potential energy has to be lowered for the product to be more stable. Think about if you have a pencil and you hold it in air and remove your finger, does the pencil go up or down?
Down.
Down, because it's more stable going downward than upward. So that means the potential energy is being lowered as it hits the floor. And there's a lot of stuff going on because it's relative force field, blah, blah, blah. Bottom line, though, is the potential energy is lower when it's on the floor. Okay, that's a more stable place for it to be than up in the air. To move the pencil from the floor to up in the air, what do you have to do to that pencil? Does it do it by itself?
No,
No.
you have to move it.
Yeah, you have to put energy in to move it. You have to supply kinetic energy, and you're going to convert that kinetic energy you put into it to potential energy up above. Remember, there's always, and as that pencil drops to the floor, it's converting that potential energy into kinetic energy because it's movement. And you can convert that movement into work and a whole bunch of other junk. Okay, so the potential energy and kinetic energy are always interplayed in a system. Okay, so let me redraw this graph. Okay, so again, reactants more stable, then products won't happen. Products are more stable than reactants, it will happen. Okay, so when that happens, tell me what happens to the products when we go from reactants to products in terms of potential energy.
They change, transform.
Yeah, in what regard? That's right, perfect answer. Just add some more to it. What happens? Does it go up? Does it go down? Stay the same?
They go down and become more stable.
Yeah, it goes down. Goes down. And remember the pencil I dropped? What changed when I dropped the pencil onto the floor? Two
It
things.
stopped moving.
Stop moving. What about things like potential energy? Did that go up or down?
Down, because there was
Down.
no more potential for it to move once it stops.
Right. And what happens when the pencil is moving downward?
Kinetic energy.
Exactly. So we're taking into exchanging the potential energy for the kinetic energy. So here, the difference in the potential energy is kinetic energy. So the PE of the products plus the kinetic energy equals the PE of the original reactants. And remember what I said about kinetic energy? What kind of energy is that?
Motion.
Motion. And
Temperature.
what is exactly? So temperature is a measurement of motion. So what happens when this reaction happens? When we go to products to more stable, so we start with reactants and go to products that are more stable, we end up with generating that. Or what's the measurement of that? What's the measurement of kinetic energy? You already said it once.
Temperature.
Temperature, yeah. So temperature goes up. So we have a piece of wood. We light it, it's burning, it produces products plus heat. That means the wood converted its potential energy into kinetic energy, also known as chemical reaction. There's one little blip in the middle here. I haven't talked about it all yet. But basically, this is what's going to happen when we have a chemical reaction. If we have this situation, tell me about this situation. Is that going to work? Remember what I said, start with stable reactants, but you got to have more stable products. Otherwise, the reactants are happy the way they are. Why do they want to change? They're already stable. So this scenario doesn't work unless we put energy into the system to make that product potential energy higher, which makes it more unstable. So this is a situation where manufacturers will make products that don't stick around very long because they're not very stable. For example, drugs. Notice there's an expiration date on our drug. That's because the product is not as stable as the original reactants. So gradually is degraded through oxidation and hydration and all kinds of manifestations, but it becomes less and less viable as a product because it changes, because it isn't as stable as what you started with. The more unstable your product, the less it sticks around. Now, in the case of wood, carbon dioxide and water is pretty darn stable. So it doesn't regenerate the wood very easily. Okay, so this concept makes sense. What we start with, it's got some inherent stability, and what we make can either be more stable or less stable. If it's more stable, it happens by itself or spontaneously. If it doesn't happen spontaneously, that means the product is unstable. And so we have to put energy into the system to make it. And it doesn't stick around because it's not that much that stable compared to the original reactants. And that's the world we live in. This is a constant thing that's going on. Constantly. We have that's why we have recycling programs and all kinds of stuff. Okay. Okay, so we talked about conservation of energy. And the other conservation law is conservation of mass. So if we start with 10 grams, we're going to do a reaction, assuming the products are more stable, and we're going to end up with 10 grams. What is wrong with this? This needs to be 60. Anyway, whatever mass we start with, we end up with the same mass, unless we have the E is equal to MC squared process going on. Now, in the case here, we end up with 50 grams of carbon dioxide in water. We should end up with 60 grams, but, and this is in an enclosed system. Same with this here, enclosed system. Okay, so we have two laws: conservation of mass, conservation of energy. Both are conserved, otherwise things happen. In a nuclear sense, we have an explosion. Excuse me, and energy is conserved, mass is conserved, and if they aren't conserved, this comes into play to make it conserved. Okay, these are some manifestations of the different kinds of energy. And this would be measured with temperature. Chemical bonds forming and breaking. Now, as far as our units go, the SI unit of energy is a joule, and you might not have heard of that. You've probably heard of calorie though. And nutrition is a big deal nowadays, and they always say this is so many calories. And there are two kinds of calories. There's little calorie and big calorie. Little calorie is with a lowercase c. A big calorie is an uppercase C, and it's really a kilocalorie. So the big calorie is equal to 1,000 little ones. So it's like a gram and a kilogram. And they don't call it a kilocalorie, they call it a calorie. Now that's not a SI unit though. The SI unit is called a joule. And of course there are conversion factors to go from joules to watts to calories, etc. The main one though is joules. We'll be using joules a lot in this class, and if you go on to Chem 400, you use it a lot there as well. Okay. So far, are there any questions about how a chemical reaction works? Different reactants to products. We're looking at different kinds of energy being conserved. We have stability arguments to be made on whether a reaction is going to go naturally or we have to supply energy.
By any chance, is there another problem that we can look at? 'Cause I'm a little just confused on what was it? Position energy, I guess.
Well, the position energy is this is potential energy,
Right.
which is the energy of position, and it's manifested in a chemical bond. And a chemical bond, we've got electrons running around the nucleus, and they interact with electrons in another atom, an adjacent atom, and those interactions have energy associated with it, and that's where the potential energy comes in, is that interaction between the two atoms' electrons. When you said another model, I mean something other than like this water example. Is that what you mean?
Yes.
Oh, sure. What would be another good example? We take iron, solid iron, and oxygen. What typically happens? We take a nice shiny nail, throw it in some water. What happens in about 2 days?
Oxidizes, rusts.
Yeah, it oxidizes, also known as rust. So this is that's what rust looks like, ferric oxide. Okay. So we start with iron and oxygen. And does this happen naturally, or do we have to do something to make the rust happen?
Submerge it in water so it doesn't happen naturally.
When you drop a shiny nail into the water, what happens naturally?
Rust.
Yeah, rust by itself, right? That means it happens spontaneously. So that means its potential energy is lower than bare iron and oxygen by itself. Remember, because the rust is more stable than iron by itself in oxygenated water. Now, the iron will rust outside of water also. Normally, people think of rust in water associated together, but the water doesn't make the rust. The oxygen gas dissolved in the water is what makes the rust. Okay, so this happens naturally. So that means the rust has lower potential energy than the iron plus oxygen gas. Now, can we convert the rust back to shiny metal?
You, I know you can remove rust from things, but does that turn it back to the same?
See, removing rust, it's still rust.
Right.
I'm saying, could we convert this back to that?
We
No.
can't.
Actually, you can, but it requires energy because it doesn't happen naturally. And so you can get rid of rust by converting the rust back to bare metal with electricity. So you do it. So if you ever want to restore something rusty, you can actually put a current on it, like a battery charger or something, a direct current, DC. You can actually reclaim the rust back into the original iron. But it requires energy because the iron is more stable than the iron by itself and the oxygen by itself. So this is going uphill. This is going downhill. So this is more stable because it's going down. This is less stable because we're having to go up because the iron is less stable than rust. Does that example help? I forgot to ask the question.
I did, and it does, yes.
Okay, cool. In fact, let's just take this one step further. How can we prevent iron from turning to rust?
Removing the oxygen from it, or
Well, okay, we back up. What makes rust?
the water, which contains oxygen.
Yeah.
Oxygen.
Oxygen, right? The water is like a kind of a carrier. So the oxygen is what makes rust. So how can we prevent rust? If you have a car that's 50 years old, that's sitting out in the field, what does it look like?
Super rusty.
Super rusty. Why?
It's been sitting out with the wind, possible rain,
Mhm.
and over time it just oxidizes and rusts out.
Mhm. And I have a pickup truck sitting out in the driveway, and it doesn't have a speck of rust on it. Why? It's 2 years old.
You said it's 2 years old?
Yeah, doesn't have a bit of rust on it. Why?
Age?
Okay. And what does age have to do with it? I agree with you. I'm just saying, but what does it have to do with it?
The length of time it's exposed to that process?
Right? Why isn't the rust forming? Now I can take my car and I could do something to it, and it'd be rusty tomorrow. In fact, it's supposed to rain tonight, which there you go. We have the water. But what would I do to my have to do to my truck to make it rusty tomorrow?
Leave it in the water, leave it uncovered? Oh,
Well, old cars out in the desert with very little rain rust. What's on my truck to prevent it from rusting?
paint.
Paint, yeah. So the old stuff, the paint is gone, not protecting the iron anymore. So the oxygen has free access to the iron, hence it forms rust. So if we can remove that, that's what prevents that from happening. Yeah, so we can do things like, how do you prevent the oxygen from happening? We can put some kind of a protective barrier around the iron. And then nothing happens to it because the oxygen can't get to the iron. That 50-year-old truck sitting out in the field, what happens is the paint has chips in it, the paint's eroded away, it exposes the iron to the oxygen, hence the rust forms. Think about Let's see. Right, got a glass of water here. What happens? Does anything happen to the glass?
No,
Why?
non-porous.
Porous. Yeah.
Glass doesn't create the same reaction as a metal does.
Yeah. Because why?
Different chemical makeup.
Right. Remember, what has to happen in a chemical reaction? Reactant product. What has to happen?
Bonds have to break.
Bonds have to break. They have to reform for the products. That's right. Good, good. What about in our graph of potential energy? What also has to happen? So what's the difference between the yellow and the red?
One goes down, becoming more stable. One goes up, being less stable.
Exactly. So, exactly. So the glass, if the glass is super stable,
Nothing changes.
yeah, that's why it remains glass. That's why glass is so nice to put stuff in, because it's super stable. It's silicon dioxide, very, very stable. So we have a glass of water in it, nothing happens because the reactants are super stable. Just a plain old glass of water. And one of the problems with glass in terms of recycling is it lasts forever because it's so stable. Now you can melt it and form other bottles and all that good stuff, but it doesn't basically go away. Same with plastic. Plastic's super stable. What happens? It forms micro, what do they call it? Microstructures, I forgot the term. But the plastic gets smaller and smaller and smaller and smaller. And then insects and marine creatures inhale this stuff, including us, because we don't even realize we're inhaling plastic all day long because it's so small. And the reason why it sticks around is because it's so nice and stable. So this concept of reactants products stability goes on 24/7, 365. I mean, it's just that is what. And Sally, your husband is a chemical engineer, right? Are you still here?
No, I don't think they're not.
No. I think her husband's a chemical engineer. He was. Anyway, that's what he deals with. Chemical engineers deal with processes, and that's what they're schooled to do. And things like this, when you're designing a reaction, how do we protect iron? Okay, well, what's the process? What's more stable? What's more unstable? You know, kind of stuff you need to look at. And okay, well, I'm going to end it here as an introduction to Unit 2, but it's a fun unit. It's very different than Unit 1. Very different. I like it much better, personally. It's not as it's. I mean, you can explain stuff in nature. You know, it's pretty cool. So, okay, any questions?
Nope.
Okay, so when I ask the questions or any questions, if I hear silence, I'm going to assume everyone's okay.